Alright, couple of announcements. Well, actually just one announcement. Project 2 is due next week, Monday. Start now, please. Please do it. It's worth a lot. Okay. And then make sure you fill out the attendance form. This is a 0. And also, again, if you want to schedule an appointment to talk about whatever the hell you want to talk about, feel free to do so up here. Okay. Does anyone have any logistical questions? Okay, so this week you guys are going to learn about runtime, which is a pretty core part of this course. Like, the next couple of midterms, or the next midterm and the final, are going to be pretty runtime heavy, so it's a good thing to know. And with that being said, yeah, any questions? Okay, so let's just jump right into number 1. And this is another what would Java print question. It has an iterator and an iterable. So this class implements 2 interfaces, and yeah, you don't have to, you may not need all the lines, but just take this should be pretty quick. I'll give you guys 6 minutes. So let's figure out what this does at 5:21. And yeah, feel free to come up if you want to talk. Wow, I took just the right amount. Woo. Okay. I'm gonna be. I'll be so sad. Hello. I don't have a worksheet for you, but I'll post a link. Okay.
Okay.
I'm sorry. All right. Let me put this. I'm sorry. I thought I grabbed a stack of 30, but it was actually a stack of... Okay, so with these problems, as usual, it's very helpful to draw a little diagram of the environment in your head, and then kind of go through it as we go along. So we're starting at the main method, so we're going to start at the scorp g equals... Can you see this? Okay. And then we have ZOI day to car array. What does that do? Yeah.
Converts the string to a character array?
Yeah. So you take all the characters in a string and then you stick them in an array. So then we're passing this into the scorp constructor, which sets contents to be whatever S is, magic character to be whatever C is, and K to be 0, right? So then here, what is contents going to be? It's going to be that character array, right? So I'm just going to type this up by doing, my bad, not R. We're going to do Z E O G I E I. Okay, good so far? And then what is the magic character? Okay. And then K is 0. Cool. So then now we run into this for each loop, right? And what this for each loop does is, does anyone know what's actually happening when I do this for character C G? Yeah.
It runs an iterator through it.
Right, so we basically get G's iterator.
Yeah.
So we call the dot iterator method, and then we keep on asking for the next thing until we run out of things to ask for. That's why we have has next and next. Are we good with that? Any questions? Okay, so let's say we get some iterator. I guess we can have this cloud be our iterator. But in this case, actually, the cloud doesn't have to be the iterator because you implement the iterator interface, you're saying that scorp is an iterator. So we just have to work with G because it is an iterator. So when we actually call for the iterator, here we just return itself, right? So we're still working with the same object G. So then it's going to say while G has something, So while our iterator has something to return, we're going to print out whatever is the result of calling next. Yeah? So then let's look at this next. So right now we do have a has next, right? Because constants.length is 7 and k is less than 7, right? So 0 is less than 7. So then we're going to go here, and it says if k mod 3 equals 0, we're going to set the index k in the contents array to be the magic character. So then is 0 mod 3 0? Yeah. So then we're going to set this to be r. And then we're going to return, we're going to increment k by 1. And then we're going to return our return character, right? And in this case, our return character is r. And then we're going to print it out. So we print out an r. Okay, so then we go through it again. 1 is not a multiple of 3, right? So the mod is not 0. So then this just stays as is. You return the character, you increment k by 1, get 2. So to prevent me running through this 5 more times, what do you think gets printed out here? Yeah, reorder. Why? Because we change every third element, or I guess every third index. So this is going to get changed to an r, and this is going to get changed to an r, right? Just by what our next method does. And then k is eventually going to be 6. Yeah. Or it's going to be 7. Yeah, it's going to turn into 7, because then we'll be done iterating. So it'll become 3, 4, 5, 6, and then 7. So then, yeah, reorder. Now when we print like a new line, sure. But then when we call on the iterator again, will anything happen? Why will nothing happen? Right, so we never reset k to be anything, right? So k is going to still stay 7, and this directly ties into the fact that g is an iterator itself, so you didn't reset the iterator, right? And so the iterator still keeps state of itself, because when you call iterator, it's just like, oh, I'm returning myself. So then k still stays at 7, and then there is no has next. Any questions? So again, you just have to make sure that you have to know what this for each loop is doing. And what it's doing is it's saying, give me an iterator for g. And g is like, okay, here's myself. And remember, in this has next method, nowhere here do we ever set k to be 0 again, right? So g just gives itself, and then you're like, g, do you have a next thing? And it's like, no, I don't, because my k is 7. Make sense? Okay. Any questions? Yeah.
So for it to call it again, you would probably do return, instead of return this, you would do return new sklark with the conditions, right?
Yeah, you could do that. You could also edit your has next to that when it stops. Or you could edit your iterator method to set k to 0 when you get a new iterator. Yeah. Okay. Any other questions? Cool. Now let's do that asymptotics problem. This one's kind of tricky, but take your time to go through all 5 of these. This should be maybe another 5 or 6 minutes. So actually, yeah, let's reconvene at 5:35. So 7 minutes. Who wants more time? Okay. So that asymptotics problem, you guys aren't too deep into asymptotics quite yet. So this is I'd say this is a hard exam problem where I wouldn't be surprised if not a lot of people got, especially the last one. So what do you guys think is the runtime for the first one? N squared. Why is it n squared? Yes.
Because both loops run in a scale of n.
Sure. So this thing runs in n over 2 time, right? Because you skip by 2. And this thing runs in n time. So then you do n times n over 2, and you get n squared over 2. But because when you're doing asymptotic bounds, constants kind of get ignored, you get theta of n squared. Okay. What about the second one?
N log n. Is that right?
N log n. So again, we're gonna look at the inner loop. So what does this run in?
Log n.
This runs in log n time, and the reason for that is because you're multiplying your counter by 2 each time. So it's gonna do something like 1, 2, 4, 8, 16. So you can see this as you're kind of breaking up a problem in half every time. In this case, you're increasing your capability to solve a problem by double every iteration of the for loop. So you don't have to do 1, 2, 3, 4, 5, 6. You can do 1, 2, 4, 8, 16, 32, so on. Does that make sense? And then this again runs in n time. So n times log n, you get n log n. And in this case, you can't just ignore log n as a constant because it's not a constant. It grows as n grows, right? So common misconception. Because you can do things where if you have n squared plus n, you can just ignore this n and then just take the bound to be n squared. But when you're multiplying n's together, you can't just be oh, it's n time because log n doesn't matter. It matters. Okay, what about this one? Yeah.
Is this log n squared? Or the same as 2 log n?
Wouldn't you be surprised at this kind of stuff?
I can see why you got that, but no. Yeah. N. Okay, so yeah, we're gonna see why is it not log squared n or log 2 log n versus n. So this is actually n, and the reason is it's pretty easy to visualize out if you draw the tree that happens. So let's say n equals 8, okay? So here n is 8, and then you make 2 calls to n equals 4, right? And then you make 2 more calls here, where n is now 2. And then you do 2 more calls here, where n is 1, right? Yeah.
Master's theorem.
Shh.
Wait, no, shouldn't it be M on M?
Huh?
Master's
No,
theorem.
it's n.
You sure?
I'm pretty sure.
Sure.
Yeah. No, cause yeah, Ming. Pretty sure.
No, because there's 8 times log n. 8 times log n.
No, but then here this is not. It's not n. It's just 1 call.
Oh,
Yeah.
oh.
Okay. So if we look here, this I just drew out the tree for n equals 8, right? And what you notice is that this is kind of turning into a binary decomposition where you just break it in half again until you get all ones. So what's going on here is we know that the lower level is gonna be n, right? Because you're gonna just have at the end a bunch of ones up to n. And then at this level, it's gonna be n over 2. So I'm counting the dots. So the number of dots. And at this level, it's n over 4. And at this level, it's n over 8. So at the top level, it's 1, and then it grows down exponentially. And the series that you guys maybe recall from the depths of your algebra 2, is that when you have something that sums to n with I equals 0, 2 to the I, this is equal to 2 to the n plus 1 minus 1. This is pretty simple to see if you just do 1 plus 2 plus 4 gives you 7. And then 1 plus 2 plus 4 plus 8 gives you 15. So that's 16 minus 1. If we add 16, we get 31, So that's the kind of series that you're getting. So then this is going to work out to be almost 2n, and then you discard the constant, and then you get n. Yeah.
Would you recommend doing the math way?
So the math way works if you like math.
Well,
The pictorial way works if it's usually for these kinds of problems I just draw the tree of calls.
Oh, so you can just do that
Yeah.
actually over.
The way I thought about it was you're recursively calling itself
could be
twice each iteration.
Mhm.
So that's 2 to the n. And then since each time you're calling it, you're doing n over 2, that's log 2 base n. So if you do 2 to the log 2 base 2 of n,
Yeah. So another way to think about it is that you're doing twice the amount of work, but each work that you're doing is half the amount of work. So if you do like 2 times n over 2, you get n. Is that?
Your job.
Okay. Next one. What is this one?
1.
Yeah, it's 1. Why? Because m is initialized to be some constant, right? So no matter what input n you give it, so notice here how m does not depend on n at all. It's independent. It's just some crazy math expression. So no matter what n you pass in, you're just going to print high the same number of times because m is going to be a constant value regardless of n. So m is independent of n.
Sorry, I just want to check on the last one. So why does 2 to the n go to n?
Huh?
2 to the n plus 1, why does that go to just n?
This part?
Or on the right, you have 2 to the n plus 1.
Oh, so this sum gives you 2 to the n plus 1 minus 1.
So how did that go into just n?
Oh, how did that go into just n? Well, this is going to be whatever n you pass in here, right? Because you're doing like I layers, and the number of I layers is log 2n. So then, because you're just like raising it again, you end up getting n. Because you're pretty much summing up to n being like log base 2 of n. So here we should probably define that n is log 2n. Yeah. Or log 2 capital N. Okay. All right, what about the last one? Any takers? This one's kind of messy, but yeah. Log n? A little bit bigger. We can like.
I got a weird one. Is it log squared n squared? It's probably not that
I
complicated.
could maybe see that, but no, it's not very complex. Yeah, it's unsquared. Okay, this one is unsquared. I think you can get a tighter bound though. I think you can get like 2 to n to the log 2. But I'll save that for later. But it's n squared, and the reason for that is we're gonna build off of the fact that this is true. And when you're doing this sort of series, what you're doing right now is doing 1 plus 2 plus 4 plus 8 plus 16 plus ... n squared, right? So then let's look at like the best case and then the worst case. So the best case is when n is going to be like 1 less than some power of 2, right? Because here you only care about like when I surpasses n. So if n is equal to like 31, you still do the same amount of work as when n is equal to 16. Or, well, actually root 31. So let's pretend it's root 31 versus like n equal to root 16, which is 4. Why? Because there's still 4 layers. You go from 16 to 32, right? And then 32 is still greater than 31. So here you guys have like the same number of loops. Does that make sense?
Wait, can you go over that again?
So here your for loop condition is that for I equals 1, I is less than or equal to n squared, and then you multiply I by 2, right? So I is only going to take on 1, 2, 4, 8, 16, 32, and 64, so on, right? So that means if n squared is 31, you're never going to hit this level. And then when n is 16, you're also never going to hit this level. So effectively, you do the same number of loops for n equals 16 and n equals 31. Why? Like, just run through it. So like, if n squared is 31, then I'm going to go through 1, and then 2, and then 4, and then 8, and then 16, right? And then I can't go through 32 because 32 is greater than 31. Yeah. So then, in the best case, like, we're getting some, we're summing, like, up to 31, right? Like, just the number of, like, little ticks that we go through for j is 31, because you do 1 plus 2 plus 4 plus 8 plus 16, and what we found here is that that's just 2 to the n plus 1 minus 1. So then we get 31 here, and then over here we also get 31, right? So best case, worst case is, or actually no, here we get 31, even though n is like 16. Yeah. Are we making sense so far? So the point is here, like, you get the same amount of work done, even though like the numbers are kind of vastly different. Yeah.
So would you calculate the runtime on each for loop, or just
Yeah. So you know here, the runtime of like these two for loops is actually just like the series, this geometric series, right? Because here you're just like going up to like whatever bound you set here, and then you do the thing. But what I'm trying to say here is that in the worst case, you're going to be summing to the next power, right? So then that means the worst case is you're going to have some 2 to the n plus 1 minus 1. And then, well, 2 to the like the n squared. Well, no. It's good. It's probably easier to think about it as you're just going to have at most 2 times n squared. So this is the worst case is 2 times n squared. And then the best case, you just have n squared. Why is this? Well, again, it's just you have to kind of get yourself into the frame, the mind, like the way of thinking where it's you go 1, 2, 4, 16, 32, 64. So like you have some gap between here where you're doing the same amount of work, right, for this range. So then I'm just calculating how much work you're doing for the best case of the range, which is the highest case, like the highest amount of work, highest n you can pass in before you have to go into another loop iteration. And then this is the worst case where, oh, you just hit the next level of n. And then here at the worst case, it's 2n squared. And then over here, it's just n squared. Does that make sense? It takes a little bit of time to like wrap your brain around the math, but so then that's why we bound to n squared.
What did you say your title was?
I think it was like n to the 1.7 or something. N to the log 2.
Log 2 is 1. Because this is log base 2. Right? Because when you do the powers of 2, it's log base 2.
Oh my god. Something like that. I don't know. Okay. No, it's not log base 2. It's, oh, n to the, okay. I'll get back to you. Alright. Are we good? You can talk to me after if you want, if you have questions. But real quick, let's just go through history map. So take like 5 minutes, 3 minutes. Okay, let's go at 5:53. So we have 7 minutes. Go. All right, let's steamroll through this one. So they give us this helper class, and because we're trying to make a history stack or like a history map. What do you think we should use this helper class for?
To store the old map.
The old map? So, or I mean, the whole map, like all history map just keeps a sequence of operations that you performed on a map, right? So then, what would we need our helper class for? Like, what are we trying to store? So we know the stack gives us the sequence, but then what do we need help with storing? Right, we need help with storing the operations. So we have to represent an operation. It would be inefficient to keep a copy of like every iteration of your map. So we want a snippy like history map, right? So we want to store a sequence of operations. But the thing is that because we're undoing, we need to store like the inverse of whatever operation that gets done, right? So that'll make more sense when you actually implement undo. So like your operation should like keep track of basically what you have to do to undo the operation that someone called. So what to undo. So then that means we just have to keep track of like a key, a K key, V val. This is getting ugly. Okay. So we need to keep track of either removing something or adding something, right? Or like adding something to what it used to be. So that means we have to introduce like basically some kind of state, which is, do we remove this or do we not? Like, do we remove the associated key value pair or do we like restore it to the key value pair? Why? Because sometimes your map operation can overwrite like the value of a key associated with a key, right? So it's just, we'll have a Boolean here of to delete. And then we'll just fill this in with like what public operation. This is just to fill in that stuff with like whatever parameters you pass in. And then now we get to the exciting part, which is for putting and removing. Because our hash map, our history map extends a hash map, we know that we can like use super to call like the actual hash map functionality, right? History map is just kind of wrapping a stack over it. So which means up here we need a stack of operations. And we'll call this history to be a new stack. So all history map is doing is giving you the functionality of a hash map, but now it has a stack of history. So it's got some state of what operations you applied. So then when we put, we know at the very end, we still have to put, right? So how do we put something into a hash map if we extend the hash map class? Yeah, so we know at the end we're going to have to call super.put key value. Now notice that history has to store like the negation of what we're doing, right? So then we need to push stuff onto our history, right? Because we just did an operation. So we'll do history dot push and then a new operation. Let's just take like the order is Boolean, key, and then value. Okay, so that's the order we'll pass into our constructor. Now, if we're going to undo what's in our stack, so if we're going to undo this action, we have to negate it, right? So like for example, if we remove something from our hash map, to negate that, we have to add it back. Does that make sense? So it might make more sense if I do the remove operation first, which is we're going to make a new operation. And because this operation is negating our current operation, that's what undoing does, it negates it. We have to say that are we gonna set to delete to true or false? False, right? Because we want to put it back in if we're gonna undo. If we're gonna pop this operation off the stack, we want to put it back in. And the reason we have to declare this in the constructor is because remember the edge case where you can replace a value in a hash map. When you're actually doing the undo part, you'll never know if that operation actually replaced a value unless you like declare it here. So false, key, and then get key. My bad. And then we do super dot remove key. Why? Because the hash map is the actual like hash map functionality. Which means if we go back up here to the put method, what is our Boolean going to be? It depends. Why? Because we want to remove it if it's our first time putting in the key, right? But we don't want to remove it if we're just like replacing a value associated with that key. So then that means our Boolean is going to be not has key. So again, why? Well, if our map does not have a key, so it's false, we want to remove it when we're undoing the action. But because if our map does have the key, we do not want to remove it. We just want to reapply like the previous state. So then that means the previous state is going to be the key and then getting the value of the key. And then you might be like, here, what if it's a key error? In Java's hash map implementation, if you get a key that doesn't exist, you just get null back. So that's why it's clean. Okay, And then now let's do the actual undo part. So over here, how do we know there's nothing to undo? Right, if our history is empty. Okay, so then now if our history is not empty, we just pop off the last operation, right? So we'll just say operation op equals hist dot pop. And then here's where our boolean is going to come in play, right? So like if we want to remove the key, so if op dot to remove, I think that's what I named it. If op dot if we want to remove the key, then we just call super and we remove the key, right? So we just do super dot remove and then op dot key. Good so far? So then else we just do super dot put op dot key op dot value. Any questions? All right, let's book it out of here.